if you go to the end of this lesson, the homework is, this isn't page 27, it's page P27, so it's before page 0, all right? So please remember, this is not a typo. It shouldn't be page 27, it's P27, like barely after the front cover, okay? All right, so this is from chapter 0. The first thing we're going to do is from chapter 0. That's where it introduces what matrices are, and then we're going to go into chapter 6. So I'm going to do this lesson, 0.6 and 6.1 today. Okay, so let's just go ahead and get started here. Let's talk about what a matrix is. Okay. A matrix is a rectangular array of variables and constants arranged in rows and columns, because that's what math people do. We don't just throw numbers everywhere. We have to arrange them in proper rows, proper columns, right? I mean, you see the big deal I make about the desks here, right? And matrices are enclosed in brackets, okay? The way that works is you've got a square bracket like this, and the matrix goes inside. In some books, or later on, you might, in higher math, you might also see matrices in large parentheses like this. For our purposes, we're going to do the square brackets, but don't get, fancy with like the curly brackets and all that stuff, okay? All right, now, each value in a matrix is called an element. Back in the day, they were called entries, and then somehow it changed into elements, but it's the same. So if you look at this matrix here, there are 1, 2, 3 rows, 4 columns. That makes 12 elements or 12 entries. All right. How do we label and talk about matrices? A matrix gets a capital letter as its name. So here, this is matrix A. All right. Yeah. And you see here how it has 4 columns. 1, 2, 3, 4 columns and 3 rows, right? Now, look at this element here, this -8. Where is its position? It's in the 3rd row, column 2, correct? So, if the matrix is capital A, each of the elements will get the symbol little a. So, and then that one, so it's little a, and then row, column. So little a, column, row 3, column 2. All right? So, if this is the first row, then these are A11, A12, A13, A14, and so on. It is understood, and it's the rule, that rows come first, then columns. This is the single most important thing you will remember. Rows, then columns, okay? Okay. Next one. Dimensions. The dimensions are the size of the matrix. And again, it's by rows and columns. So for the dimensions, we use M and N. The common convention is a matrix has M rows and N columns. So the dimensions will be written like this. It's the X. M by N. So that's how it's read. So this one here, if it has 3 rows and 4 columns, the dimensions here are 3 by 4. If you say 4 by 3, it looks like a completely different matrix, right? Okay. Now, so take a look at this one here. We have a large A matrix. First it says to state the dimensions of A. So how many rows here? Go down 1, 2, 3, 4 rows. And how many columns? 6 columns. So this is a 4 by 6. Okay. Find the value of the following elements. So where is A, 2, 3? Second row, third column is 0, 3, 5, and 4, 6. Yep. And 1, 2, negative 3. Okay? All right. So, different types of matrices with special names. A row matrix, guess what? It's a matrix with one row. Look at that one. Okay, that's a row matrix. What are the dimensions of that matrix?
1 by 4.
1 by 4. A column matrix is a matrix with one column, such as this one. That's a 2 by 1. Guess what a square matrix is? It's a square, same number of rows as it has columns, right? So, same number of rows and columns. So this is a 2 by 2. A zero matrix can have any dimension, but it's just that all the entries are zeros. Okay? By the way, a square matrix, the general case, we also say like n by n. So, you know, often you'll hear people say, so in an n by n matrix, that's a square matrix. An identity matrix, okay, is a matrix in which every element on the main diagonal is 1. Okay, so what is this main diagonal? The main diagonal, so this would happen in a square matrix. The main diagonal starts with the first entry, 1, 1, and then it's that diagonal. There is no other way to draw that a diagonal, right? If you start with 1, 1, that is always the main diagonal. It doesn't go the other direction because it starts with the first element. That's the main diagonal. An identity matrix has a main diagonal of 1s and everything else is zeros. You'll learn later what that means. Okay? Yeah. It has to be what? A square? Yeah, because then you can't really draw a diagonal. Like you'll have a row left over. Okay. So let's talk about matrix operations. How do we add or subtract matrices? All right. So they can only be added or subtracted if they have the same dimensions, period. Why, you ask? Because if you have a matrix A and if you have a matrix B, the way you add them is like how you add vectors, right? If you have a vector with 2 components, can you add it to a vector with 3 components? No, because the first components match, the second matches, and then the third will be left over. So same thing here. Huh? Yeah. So look at how you do it. This is matrix A. You take the first with the first, and it goes in the first spot. And then you take the second with the second, and it goes in the same spot. Okay? Subtracting is the same. So let's just do one. So look here. We want to add A and C. Well, this is A. What are the dimensions of A? 2 by 2. B is a 2 by 2. What about C?
1.
A 2 by 1. Rows and then columns. So A plus C, it's not possible, right? So you just say not possible. B minus A, that I can do though. So this is B. And then this is A. Minus 1, 3. If you have 2 by 2s, your result is also going to be a 2 by 2. And so now you take the first 10 minus 2, 8. I love matrices. Like, you have no idea. Like, oh my God, I love matrices. Okay. Negative 2 minus 5, negative 7. It's so much fun. Negative 3 plus 1. And then 16 minus 3, 13. Yeah, so 2 by 2, 2 by 2, and then the result is also a 2 by 2. Yep.
What are matrices? Like, I know, like, you described, like, where do they come from?
So it's a way of organizing information. It can be, for example, as simple as like there is a store and they have different types of CDs or different types of products for different prices. All right? It could be something as simple as that. Okay? It could be, like you'll see examples, like it could be, for example, if you have like a 4x3, it could be like, freshmen, sophomores, juniors, seniors, and then like, organized by, whatever parameter. All right? It's a way of organizing information. Okay, scalar multiplication. Geez, where have we seen that word before? Scalar multiplication. What's a scalar? It's just a what? It's just a number. Scalar multiplication, just like matrices, vectors. You just distribute and you give one to each. So if we multiply this, then, you just distribute to every single element. So -3, going down, 0, 18, -15, 6, -12. Is that okay? So far, so good, right? Okay. These properties are still the same. Commutative property is the same. Associative property is the same. If you're adding 3 matrices, you can do them in any order. Scalar multiplication, you can distribute. It's the same. All right? So why don't we do one of these here? I have to do 3 times A minus B. Right? So you can either do 3 times A minus 3 times B, or you could do it in the other order. So this is going to be 3 times. Okay, so what's A? That's A minus B. And now look at what I'm going to do. It's going to be 3 times the whole thing here. Okay? And you can do that. You could do brackets and then parentheses. We alternate brackets, parentheses, brackets, parentheses. And so now this is 3 times. And what's the difference of these matrices? 4. I'm going to go across -2, 1, -3, 4 minus 4. Distribute 12, -6, 3. -9, 12, -12. Fun, right? Okay, it's very straightforward. Okay, so now let's talk about equations, because that's what we do, right? Okay, your entire life you've been solving equations that look like this. 3x minus 6 is equal to, 10. Okay? 3 is a number, 6 is a number, 10 is a number, so x is a placeholder for yet another number. So when I solve for x, what do I get? I get a number, right? A scalar, right? Because this is a equation over real numbers. But now, if I have a matrix equation and not a real number equation, and in this case, the key players now are matrices. And now when I solve for x, I don't get a number. My x is a matrix. Okay? So, in these cases, again, the solution will be a matrix, not a simple scalar. Okay, so how do we solve matrix equations? Well, guess what? You algebraically solve the equation for x. Notice, I have a capital X. That stands for a matrix. Capital X means matrix. So we solve the equation for x, and then we substitute in order to solve for it. Okay, so I'm given a matrix A. I'm given a matrix B. I need to solve this for x. Okay, so let's do that. So let's get the equation 2x minus A is equal to B. And I want to solve for x. So I add matrix A, 2x is A plus B. Then I need to divide by 2, so x is 1/2 A plus B, right? We don't say A divided by 2, we say half of matrix A, okay? So here's what x is then. X is 1/2 of matrix A plus matrix B.
What you never say divided by?
It's the same, yeah, it's like 1/2 of, yeah, we don't really, I mean, I guess with numbers it's okay, there is no such thing as dividing matrices, period. And so, yeah.
So if I did,
It's very unconventional to have a matrix divided by a number, that's not really a thing.
is this wrong? Would this be wrong? Or is it fine?
It's unconventional, I guess it's okay. We usually solve it like this and then plug it in, it's fine.
Okay.
But it's cleaner like this. Okay? Alright, so go ahead and finish this one. I have a 2, 1, -1, 4. Are we all in agreement? That's matrix X. Awesome. Okay? So, the homework from this is this. To remember, this is page P27. Okay? If you're solving from page 27 and there are not any matrices to be found, you're on the wrong page.
Do you want 2 separate assignments?
Yeah. 2 separate assignments. 6.0, 6.1. You can do 0.6, 6.0, I don't care, and then 6.1. Alrighty, so now that we've got matrices, how do we use them? Why do we care? What happens? Alright? Okay. We're going to talk about systems of equations. Do you remember way back when you learned how to solve systems of equations? X plus 2y equals 7, 3x minus y equals... And then in Algebra 2, you learned how to do it with 3 variables. Remember? X, Y, Z, X, Y, Z. It was in Chapter 3. You only did the 3 sections from Chapter 3 and then you took a test very quickly. Alright, so you learned how to do it, using the variables there. Here we're going to learn how to do the same thing using matrices. Okay? Alright, one way is Gaussian elimination, and it's named after the physicist Gauss, Carl Friedrich Gauss. He is responsible for doing a whole bunch of things with magnetism, and actually Gauss is a unit for magnetism. There's Tesla, like to measure the magnetic field, there's a Tesla and then there's a Gauss, because these two, the same Tesla as the car, as the person that the car is named after, and Gauss, they worked, like they were contemporaries. And so like 1,000 Gauss is a Tesla. No, 1,000 Tesla is a Gauss. Okay? Alright. So, when you have a multivariable linear system, so a linear of equations in 2 or more variables, you can use substitution or elimination to solve for a matrix, to solve for the variables, right? One thing we can do is, when you start out with 3 equations and 3 variables, you can start from the bottom and start eliminating the variables, eliminating the terms. So here, the third one, you eliminate x and y. In the second one, you eliminate y. And then what you end up with is this triangular looking system. Okay? We call that, when it's in triangular form, we call it row echelon form. So that is in row echelon form. The process we use to get there is called Gaussian elimination. Okay, it's a little bit different from what we've seen, but we're going to do it today. Notice here the leading variables, or the leading coefficients, are 1. Okay, so what are some things you can do here? There are some operations you can do that are free of charge, okay? One thing you can do is interchange any two equations, right? You can swap them. You can multiply one equation by another number, like multiply through by 2. You can add two equations to each other. Remember how you used to multiply 1 by 2 and then add it to the other one? Okay. So, I've come up with like the most hassle-free system to put something in row echelon form. And here's how it works. First, eliminate the x term in equation 3. Okay, so we're going to use this. We're going to go one by one, and we're going to use it to solve this system here. Okay, so first, we're going to eliminate the x term in equation 3 by replacing equation 3 with itself and something else. Okay, what the heck does all that mean? So look at this here. Okay. Huh?
Is this equation 3?
This is example 1. In example 1, I have equation 1, equation 2, and equation 3. Okay? So take a look at what I'm going to do. What I want to do first is I want to get rid of this element, right? Remember how over here I say eliminate the x term of equation 3. That's what I want to get rid of. So, here's what's different about this. What I have to do is, the one that I'm trying to get rid of, right, that's in equation 3. I'm not going to get rid of equation 3. I'm going to replace equation 3 with a combination from the other ones. So, how can I get rid of this x? What can I do? Can I do equation 2 minus equation 3? Will that get rid of that x term? Right? If I do this minus, so just look at the x's here. How can I get rid of this? Well, I could do that minus that, right? So, I write a little note for myself, and I say equation 2 minus equation 3. Okay? And I'm going to replace equation 3 with that. So if I do equation 2 minus equation 3, I'm going to get 0, 0, minus 2z equals negative 5. Right? Yes? I wanted to get rid of this x. How can I get rid of, just look at the x column. How can I get rid of it? Well, if I subtract these two, that gives me a 0, right? So basically, how do I get a 0 for that term? That's what I did. Okay, so I didn't touch anything else, so I just copy them over. Okay? Now look at what it says to do next. Now it says to get rid of the x term in equation 2. So, the x term in equation 2, how can I get rid of that? I'm going to get rid of this one now. Okay? Everything else is going to stay the same. So what I can also do is copy down everything else. This one is 0, 0 minus 2z is equal to negative 5. Now I'm going to replace this one. But how am I going to get rid of it? So just look at this. Look at this x column. That's what I'm trying to get rid of. What combination will give me a 0 here?
Multiply that by negative 2.
Yeah, it's z. Okay. Multiply it by what? Negative 2, and then do what? Multiply this by negative 2 and then do what? And add it to this, right? So what I'm going to do is, I'm going to do equation 1 minus 2 times equation 2. Is that right? So now look at what happens. Equation 1, 2x, minus 2 times this is what? 0. And let's do it again. I'm going to write it down. So 2y minus 2 times y is what? 0. And then 3z minus 2 times z, no, minus 2 times negative z, 5z equals, now you have to do it to the constant, 6 minus 2 times negative 3, 12, yeah. Huh? Okay. So now, from here, we would like solve for one of them, right? And then eventually plug it back to get the other ones. So this particular one actually will not have a solution because both of them got rid of the y's. Okay? So that's pretty much the process. And then we put everything back and we solve for the other ones. So now, this is how it would be done with the variable still in there. Now let's do one, but with matrices.
So that's the final answer?
No, it's halfway through. I showed you how to set it up because I really want to do it using matrices, but I was showing you like how it looks with the equations. You know what I mean? Okay, now, we're going to actually solve, this is the matrices chapter, we're going to actually solve these using matrices. So, you notice here, you're just copying down XYZ, XYZ, XYZ all the time. The only things that are changing are the coefficients, right? So what we're going to do is we're going to convert the equations into matrices, and then we're just going to solve the matrices. So look at how that works. You can take the system of equations, and you just take the coefficients 5, negative 1, 3, negative 5, 2, negative 2, right? And you convert it into a matrix. This is called an augmented matrix because after the coefficients here, you've got a dotted line and then you've got what they equal, the constants. Okay? This is just the coefficient matrix. Okay, so we're going to do the same thing with matrices now, and we're going to convert them to row echelon form. The same operations as before apply here. All right, so look at this. What does row echelon form look like in matrices? Basically, you should be able to write a matrix like this. If you have any rows with all zeros, you put it at the bottom. And then you should get a triangle here with 1, 1, 1. So take a look at these. Are any of these in row echelon form? So basically, if you get the diagonal, the main diagonal, are they all 1s with everything underneath 0? Does that qualify? Yeah, so this is in row echelon form. How about this one? Is this in row echelon form? No. Next one. There I have a leading diagonal. I have a row of all zeros, but it's placed on the bottom, so yes, this qualifies. Okay.
Oh, there could be a row of all zeros.
Yeah, in row echelon form. Okay, so we're going to do the same thing here, but we're going to use matrices. Again, tips and tricks. Start with A31 and then move up. So let's do this one here. First, I want to put this into matrix form. Okay, now, you don't have to do this, but it's always wise to do it. If you see a row that can all be divided by the same number, divide it by the same number. So first, divide everything here by 5. And then I'm going to write the matrix. 1, minus 1, minus 1, 7. Minus 1, 2, minus 3, negative 12. 3, negative 2, 7, 30. Often this is where a student will make a mistake, is like copying it down and then it all goes wrong.
Doesn't have to be a dotted line.
No. Okay, now, I say here to start with element A31. That's this one. Okay. If that's the one I want to get rid of, that's the row that needs to change. So what I do is I copy everything else exactly as it was. Later on, we'll learn how to combine steps. Okay, that's the row I'm changing. Again, I want to call these row 1, row 2, row 3. Always keep track of what you're doing, right? Okay, how do I make that 3 into a 0? How can I combine? So here's what I want you to do. Look only at the first column. How can I combine the 3 with one of the other numbers in order to get a 0? Multiply row 2 by 3 and add it to this, right? So write that down here. 3 row 2 plus row 3. So here I get a 0. And then 6 minus 2, I get a 4. And then negative 9 plus 7, negative 2. Negative 36 plus 30, negative 6. Okay? All right, what do I say to do next? Eliminate A21. Next, I want to eliminate this one. Is this like the law? No. It's very helpful to do it this way, though. Okay, in this order. Okay, so next, how am I going to get rid of that one? You just have to add 2 rows, right? So let me just copy whatever I'm not changing. Again, please write down what you did so you could go back. So we're just going to do row 1 plus row 2. 0, 1, negative 4, negative 5. Next, I need to get rid of this one, A32, this guy. Okay, copy everything else.
Isn't negative 4 not negative 3? Negative 1, 2, and negative 4.
Where?
So you're adding them. And it's negative 1 plus negative 2.
Wait, which column are you looking? Which one are you looking at?
The other one.
Am I okay? Yeah? Okay. Here, so what are we going to do here? How am I going to get rid of this? That 4. Okay, so here's a question for you. Now I need to change this 4. Can I use row 1 and row 3? What happens if I add row 1 and row 3, or multiples? What happens to this quarter 0? It becomes a non-zero again. You've just undone what you did. So at the last step, the reason why I do it this way is because at the last step, I can just use the bottom 2 rows and it's easier. So row 2, so 4 times row 2 minus row 3. 4R2 minus R3. 0, 0. And then, so that's what? Negative 16 plus 2, negative 14. Is that right? And then here I have negative 20 plus 6, negative 14. Now, I'm almost there. I'm almost there. What I need to do is I need to make all that main diagonal 1. So now I need to just divide the bottom row by negative 14. So negative 1 over 14 times row 3. And I get 1, negative 1, negative 1, 7, 0, 1, negative 4, 5, negative 5, 0, 0, 1, 1. Now, this is in row echelon form.
Wait, why did you do it by 1?
Because the rule is this main diagonal has to be all ones.
So wouldn't it be 1 over 14?
Oh, I meant, I said 14, I wrote 4. Row echelon form, or REF for short. Okay, now here's what we do. This, remember, was the first column was the X column. Then the Y column, then the Z column. So the way I can read the first row here is 1x minus 1y minus 1z equals 7. 0x, 1y minus 4y minus 4z equals negative 5. So now what I do is I start from the bottom row. Start from here. And what does that tell me? Z is equal to 1. Okay? Then substitute into row 2. And I get y minus 4z is equal to negative 5. Y minus 4 times 1 is negative 5. So what's y? Negative 1. Then substitute into R1. X minus y minus z equals 7. X minus negative 1 minus 1 equals 7. What's x? 7. Now, oh my gosh, what have I been doing this whole time? When I have an equation with 2 variables, linear equation with 2 variables, it's a line. 3 variables, it's a plane. What I have found is the intersection of 3 planes, and that happens at a point. So if you look at this corner of the room, one wall, another wall, and the ceiling, 3 planes intersect at that one point. These 3 planes intersect at a specific point in space, specifically at coordinates 7, negative 1, and 1. Okay, let's do some special cases. Yay! Okay, when the matrix can't be written in row echelon form, it's either no solution or infinitely many solutions. And you guys know that from the 2 variables, right? They are either parallel or they lie on top of each other, so it's infinitely many. Okay, so let's do this one. 1, 2, 1, 8. And I'll show you how to go a little bit more quickly here. Okay, first thing I'm going to do is change this, right? And I'm going to write the replacement in the 3rd row, correct? Okay, how am I going to get rid of this? Well, you know what I'm going to do? R1 minus R3. Can I do that? Sure, why not? 0, 1, 3, 3. Guess what? Next.
So why is it 3? Because it's 1.
I'm just, next, I need to get rid of that one, right? I can do it in the same matrix because they have nothing to do with each other. So, how can I change 2? And guess what? I can, use any of these. So how can I change that one? What can I do?
Multiply row 1 by 2 and subtract.
So, 2 row 1 minus row 2. Right? 2 minus 2, 0. 4 minus 3, 1. 2 plus 1, 3. And then here, 16 minus 13, 3. And then I have 1, 2, 1, 8. Oh my. Look at what I got. What did I get? Yeah, so 2 identical rows, infinitely many solutions. If you say all reals, you're wrong, right? Because it's not all reals, it's just infinitely many solutions. But do we stop there? No, we don't. What do? You take that guy and you say y plus 3z equals 3. And you solve for y. I'll show you why you solve for y. So y is 3 minus 3z. Then you go to equation 1 and you say x plus 2y plus z equals 8. X plus 2, what's y?
3 minus 2z.
Plus z equals 8. You solve. X plus 6 minus 6z plus z equals 8. Guess what x equals? 2 plus 5z. So now, you have x, y, z. What's x? 2 plus 5z. What's y? 3 minus 3z. What's z? Just z.
Why is Z just Z?
We always write it in terms of one variables. It's convention to do it with z because with z is the first one you're solving for.
And then you just plug it in.
That's it, you're done.
Why can't you plug those in?
There's nothing to plug into.